Hi, everyone.
Hi.
Okay, can you please see if you're able to share your screen?
Yes, should I try first and then after Philip can try and directly take over maybe?
You're the first one, right? So yeah, so Philip, maybe you can share your screen.
Let me try. Do you have my screen?
Yes,
Yes.
we have your screen.
Great.
So now let me try.
Yeah, let me unshare.
Okay, perfect. I think you can see my screen. I don't have my slides up, but it's there, right?
The screen, yes, you can see.
So I can stop
Yeah, we can see
sharing.
your screen.
Yeah.
Okay, try as well.
Yeah, you just share your screen and you can we can start in a minute or so.
But I think Philip is the first speaker.
Yeah, I guess
Sorry?
so. That's what the program says.
Okay, let's follow the program then. Okay, so each have assigned 25 minutes. You can go to 25 or stop at 20 if you want to leave some room for questions. And okay.
That's good.
Yeah, so maybe I'll share my screen
so,
again.
Yeah, I think it's time. I don't know whether we can give a minute if someone. Okay, so thanks for participating in this session. So we go just straight ahead. Please, Philip, start with the first presentation.
Yeah, thank you, Fernando. Hi, everyone. This is joint work with Kiminori Matsuyama from Northwestern. I am from HEC University, St. Petersburg in Russia, and the title of the paper is Constant Pass-Through. So in brief, the motivation for this paper is as follows. You have probably seen at least once what they call standard pass-through regression, the term coined perhaps independently by Gopinath and Rigobon and Nakamura and Zerom. The regression is very simple. Like you have log price on the left-hand side of the equation, and you have some proxy of log marginal cost. Usually you run these regressions using firm level data with some coefficient, plus you have something else, other regressors, control variables, plus you have the error term as usual. So the object of interest here is the pass-through rate, which is whenever you run a regression like this, you want to study pass-through, like the impact, the elasticity of price with respect to marginal cost or any kind of proxy of marginal cost. Well, it could be like some exchange rate shock, could be changes in energy prices, whatever. But the point here is that whenever you run a regression like this, you implicitly assume that this pass-through is actually constant and common across firms in your SEM. However, there is empirical evidence that larger firms, in fact, have lower pass-through rate in recent papers by Amiti, Tzhoki, and Koenigs and some other authors. They use non-parametric approach to capture this, and they microfound it by assuming that larger firms are actually strategic and granular. However, this evidence is still compatible with assuming constant pass-through, even though not common across firms, even if we want monopolistic competition where all firms are non-atomic. Okay, so question is, could we rationalize these co-path and co-path assumptions within monopolistic competition? Could we rationalize these properties? And the answer to both these questions is yes, and this is what the paper does. So brief introduction. Monopolistic competition with CES is a workhorse model in many fields, but given full credit to the merits of this model, it has a number of strong restrictions, and one of these restrictions is that if you do CES with monopolistic competition, you have complete pass-through. And also, this restriction extends to multi-sector settings with nested CES, so you cannot even make pass-through sector-specific, not to mention that you cannot make it firm-specific. So we propose and characterize parametric families, which we call co-path, constant pass-through, and its special case co-path, which is constant and common across firms pass-through, and the further special case of this, which is constant price elasticity, CPE. These functional forms actually feature a constant pass-through rate as a parameter for each monopolistically competitive firm, and they accommodate a single measure of toughness of competition. They allow for endogenous markups and incomplete pass-through and strategic complementarity, which are all features found in the data. These functional forms also allow various types of heterogeneity across monopolistic competitive firms, and these heterogeneities are not isomorphic to each other. With constant and common across firms pass-through within a sector, we could still have sector-specific pass-through. So pass-through could be different in different sectors. With co-path, tougher competition has no effects on relative prices of firms within one sector, but reduces the relative revenue and profit of firms with lower markup rates. Note that this does not necessarily mean firms with lower markup rates are smaller or less productive, because we really allow for a number of dimensions of heterogeneity. It's not just standard Mellitz-like heterogeneity in productivity. Okay. And these families retain much of tractability of CES, so they are a useful building block for a wide range of monopolistic competition models in macro, in trade, and potentially other fields. Okay, so this is just a brief explanation how exactly our findings relate to the literature. Like, long ago, there were not many alternatives to Cobb-Douglas production function, but at some point, Arrow, Chenery, Minas, and Solow realized that a tough restriction, which makes this production function rather counterfactual, is that the substitution between labor and capital is equal to 1, and the budget shares implied by this production function are constant. So they came up with a constant elasticity of substitution. But constant elasticity of substitution necessarily implies complete pass-through. So we successively developed 3 extensions of CES. One is CPE, which still implies a complete pass-through. The other one is co-path, which gives you incomplete pass-through, but constant and common across firms, at least within a sector. And the third one is co-path, where the pass-through is constant in that it's not responsive to various general equilibrium effects. You can really think of it as a parameter, but it's a firm-specific parameter. Okay, and we develop. I'm not really going to talk much about this for the interest of time, but this is basically about the tools we use to develop these parametric families. We actually come up with 3 versions of this constant pass-through families. One is within, so each version is related to a certain class of constant returns to scale production functions, which we developed in our earlier paper with Kiminori 2017. So one class is homothetic with a single aggregator. The other class is homothetic directly implicitly additive, which is basically an extension of Kimball's flexible aggregator. And the third one is the dual version of HDIA, homothetic indirectly implicitly additive. Okay, so a frequently asked question we get, is it even worth bothering, given that the empirical evidence gives you the idea that larger firms tend to have a lower pass-through rate? How good the assumption of COCO path actually is, how relevant it is, etc. So, well, first of all, large firms may have lower pass-through due to oligopolistic behavior, and so if your research question is such that you would like all firms, or at least a positive share of firms, to be monopolistically competitive, then actually working with COCO path is less of an issue. So you just focus on firms which are monopolistically competitive, and also you still could make a pass-through variable across firms in the cross section if you have a multi-sector model where pass-through is sector specific. Also, COCO path is definitely an improvement compared to homothetic translog people use in many applications, because the implication of a translog is that actually pass-through is higher among larger monopolistically competitive firms. At least this is so if monopolistically competitive firms only differ in productivity. So if anything, translog is more severely counterfactual than COCO path. So at least it's an improvement, and it's an improvement which still offers you a lot of productivity, a lot of tractability, sorry. So even though we don't really believe pass-through is literally constant across firms, this could be a useful modeling choice, which at least shows more accordance with the data than the translog does. And as long as people use translog, why not use COPath, right? So this is our general setup. We basically do monopolistic competition with within a production factor, which consists of competitive firms producing a final good and assembling it from a continuum of intermediate inputs using constant returns to scale technology, and at least a subset of positive measure of intermediate input varieties is produced by monopolistically competitive firms. We could allow here for also multi-product firms, but in the baseline model, we just do single product firms. Let me skip this for the interest of time. I'll just say here that the key object of interest is the price elasticity of demand, right? Which is a function, price elasticity of demand for variety omega is the function of the own price of the variety and the whole vector p bold of the prices for other varieties. So for the three classes I mentioned before, there is this useful property that how the elasticity of the answer to the question how the price elasticity of demand depends on the cross price effects is very simple. Instead of this whole array of prices on which in general the elasticity could depend in a rather hairy way, we have only just a scalar price aggregator, which is some kind of average price, linear homogeneous price. And the demand elasticity only depends on this kind of normalized price or relative price, which is the own price over the price aggregator. Okay, so this is just a textbook learner formula because we assume monopolistic competition. Each and every firm charges profit maximizing price according to the learner formula. And under some regularity conditions, you can safely solve this equation with respect to the normalized price, which is the own price over the price aggregator, and obtain this normalized price as a function of the relative firm-specific relative marginal cost or normalized marginal cost. So here psi of omega, psi subscript omega is the marginal cost of the firm producing variety omega. And also you can express the markup rate as a function of the relative or normalized marginal cost. And also you can express the pass-through rate, which is by definition the elasticity of the firm's price with respect to the marginal cost as a function of the same magnitude. Okay, so if you're willing to have this exogenous, independent of equilibrium variables and hence irresponsive to general equilibrium effects, this is what the pricing formula actually becomes. And basically our exercise is to reverse engineer the primitives of the model, the fundamentals, the production function basically, or the unit cost function, which it is equivalent to specifying the production function by the duality principle, right? So we reverse engineer this kind of fundamentals within each of the three classes of production functions I mentioned before. And in doing that, we allow for a number of heterogeneities. So you see in this pricing formula, we have a product-specific markup shifter sigma omega. We have price or quality variety-specific shifter beta omega. We have heterogeneity in the marginal costs across firms. We have heterogeneity, exogenous heterogeneity in pass-through rate. And one other source of heterogeneity, which is not in the pricing formula, but it still shows up later, is the market size shifter, gamma omega. And also we have this element which is common across products within the sector, which is this price aggregator, linear homogeneous in prices. And the role of this price aggregator is that it captures toughness of competition in the industry or in the sector, whatever. Okay, so this is the complete pass-through case, the constant product-specific price elasticity case. And in this case, the pricing formula becomes exactly like for the CES, except that here the demand elasticity, the price elasticity of demand can be firm specific. So here sigma is no longer the elasticity of substitution, which is common across varieties, but it's constant but firm specific demand elasticity. That's the difference. Okay, so CES is a special case when all the price elasticities are common across firms. Okay, so for the case of incomplete pass-through, what do we have here? We can restate the pricing formula as follows. So you see it's a nice log linear expression which relates the profit maximizing price to the log of the marginal cost of the firm specific marginal cost with weight rho omega, where rho omega is the firm specific pass-through, and the log of the choke price, or the relative or the normalized choke price, right? Which includes the common price aggregator and also various other sources of heterogeneity, the price shifter or quality shifter, the markup shifter, etc. Okay, so here this equation looks pretty much like the standard pass-through regression, except that it somehow disciplines the way we think about this standard pass-through regression. Under COCOA-Path, it literally becomes the standard pass-through regression because this guy now becomes common across firms, so we could really estimate it as a regression parameter, okay, a regression coefficient. But the difference here is that okay, we have an understanding where other variation in prices not related directly to the pass-through rate, firm level pass-through rate, could come from. It could come from quality shifters or some other sources of heterogeneity. Okay. Yeah, so just a second. Yeah, so if you look under this COCOA-Path structure on what happens to the relative prices and the relative markups, here both of them turn out to be independent on the price aggregator, on the toughness of competition. So this is a great advantage when studying the general equilibrium effects of shocks that change the relative cost across monopolistically competitive firms, which could be, again, anything. They could be changes in the exchange rate, changes in tariffs, changes in energy prices, etc. So under COCOA-Path, the impact of such shocks on the market rates, on the markup rates and relative prices can be actually calculated without worrying of feedback effects imposed by general equilibrium. Fernando, how much time do I still have? Like 3 minutes?
Yeah, exactly. You have 3 minutes.
Okay, great. Great. So also we can actually see quite clearly how toughness of competition affects relative revenues. So under incomplete pass-through, we have this kind of expression, which is actually log supermodular in firm-specific cost and the price aggregator. So we can find that firms with lower markups, which are, again, not necessarily smaller firms, because it's not just Melitz-like heterogeneity, but other type of heterogeneity. Also, we allow also for other types of heterogeneity. So firms with lower markups suffer more from tougher competition. A lower average price, which means tougher competition, reduces stronger the revenues of firms with smaller markups. And same thing is true about profits. So if you think of firms with lower profits rather than with lower revenues as smaller firms, the same result actually holds. Yeah, actually, I still have 1 minute to show you how exactly the COPATH families under the 3 classes look like. Let me just briefly remind you that the 3 classes are HSA, homothetic single aggregator, HDIA, homothetic directly implicitly additive, and HIIA, homothetic indirectly implicitly additive. So basically, we just yeah, let me because my time is almost up. Let me just talk about one of them, HSA, which is most tractable. So the great thing about HSA is that we can fully specify the demand system and actually integrate back to the production function by just specifying the market share as a function of the normalized price. So if you have this function, the market share function, which only depends on one argument, the own price over the price aggregator, you're basically done. And for yeah, so yeah, and for to get this COPATH thing, all you need is to specify this market share function in this particular way, where you can see all the sources of heterogeneity, including the market size heterogeneity, which didn't show up in the pricing rule, but it does show up in this HSA specification. And the last thing to say here is that HSA is actually great for empirical work because it relies on specifying the market share and data, firm level data about market shares. You have data on prices, data on profits, not necessarily, but data on market shares, yes. And this kind of makes HSA particularly appealing for empirical work. Okay, I guess that's it. And yeah, thank you for your attention. And I stop here.
Thanks a lot. So now we have Lucas. Please, Felipe, stop sharing your screen so Lucas can take over.
Okay, yeah, thanks a lot, Philippe. It was very interesting. So I will present joint work with Kohei Iwasaki and Randall Wright. So Randall Wright, many of you maybe know, he's at Wisconsin, and Kohei was his student, and he's now at Osaka in Japan. So this is about economies with multiple assets. So basically, like the current frontier of models in monetary and financial economics are GE, general equilibrium models, where payments are taken seriously, liquidity is endogenous, and there are multiple assets. And there are already many papers that consider steady states with 1 or 2 assets or dynamics with 1 asset. But we want to go a step further. So we have a model with 3 assets actually, and we examine both steady states and dynamics. So we go beyond current work on both dimensions in steady states and dynamics. So the assets we have in the model are fiat money M, so that's cash basically. We have reproducible capital K, and we have real long-lived assets, think of them as Lucas trees. Importantly, they're in fixed supply capital A. In the appendix, we also study short-lived assets and bonds. So this could be extended to other assets or more assets without many problems, but yeah, the results apply. And basically what we find is having more assets generates more interesting results, especially more interesting interactions. For what I'm going to show you today, we'll have models where A and K are also can be traded directly against consumption. But some people might prefer models with financial markets where if you have A and K and you want to get consumption, you first trade them against money, M. And we also consider that in the paper, and we show that under some conditions, the results we have are actually equivalent with a model where you first have a financial market where you trade these assets against money. Okay, so for steady states, what we do is we study the effect of inflation on, for example, investment and equity markets. So in the model, we have a non-degenerate return distribution across all these assets, and we can show how these real returns depend on monetary policy, which follows an IDN-Wallace. Like in general, typically inflation, higher inflation will, of course, lower the return on money, but it might also lower returns on other assets. We can study things like the Mandel-Tobin effect, and we show that it actually depends on properties of all three assets when three assets are present. And yeah, just generally speaking, having money, assets, and capital allows to consider these phenomena in integrated settings and shows how effects are interdependent. And in terms of the dynamics, we show that there exist belief-driven cycles. This has been known for monetary models for a while with one asset, but we extend this to multiple assets. And one result we have is that in the setup we use, at least, capital cannot cycle if it's the only asset in the economy. But once it competes with A or M in the payment process, it can also start to cycle in equilibrium, in these dynamic equilibria. And of course, money and assets, they can already cycle when they're the only asset. But when we have multiple assets, we can find more patterns. So we can find equilibria where the volatility of each asset's price and return can be high or low. We have different correlations. And also an important finding is that the time series patterns coming from these dynamic equilibria might not match the comparative statics. And that's, I think, we think a nice example of the Lucas critique. Yeah, this is more motivation, but I'm going to skip it in the interest of time. Instead, let me tell you the contribution. It's about monetary policy. So in the model in steady state, pegging the growth rate of money, the inflation rate, certain interest rates, or measures of liquidity is all equivalent. And we can show then in a quantitative exercise that, for example, monetary policy can move real returns from 5% down to 2%. And we also calibrate the model to US data. And we show that having multiple assets actually increases the welfare cost of inflation, but it reduces cost of eliminating cash. So the reason with multiple assets that the welfare cost of inflation goes up is actually when we fit money demand. Like if money is the only liquid asset, then to fit money demand, the transaction value, liquidity value of all assets in the economy gets underrepresented, because only then it's possible to match money demand. But when there are other liquid assets in the economy, then the total activity in these markets where liquidity is needed becomes more relevant, and that then makes inflation more costly, because inflation not only lowers return on money but also on other assets. For dynamics, we show that when M is not the only liquid asset, when money is the only liquid asset, then a nominal interest rate peg entails uniqueness. So you can eliminate dynamics when M is the only liquid asset by following an interest rate peg. But this result does not generalize, because when we have multiple liquid assets, then even if the central bank pegs has a nominal interest rate target, there can still be cycles. Okay, so there are some examples from the literature, but let me jump into the model. So the environment is based on Lorentz and Wright and Rostow and Wright. Time is discrete and continues forever. Each period is divided into two sub-periods. So this is the standard Lorentz and Wright setup. So we have a DM, decentralized market, and a CM, a centralized market. And we have two types of infinite lived agents. We call them buyers and sellers, but we are agnostic about the interpretation of what these agents really are, because importantly, like we want to have a model of all types of payments. So you can think of them as households trading with each other, You can also think of them as households trading with firms, or firms trading with each other. You can have investors and banks trading with each other, or banks trading amongst themselves. All of this has already been done in the literature, and for our application here, as I said, we are agnostic, and you can interpret this as any of these types. So in the DM, buyers meet sellers with some probability alpha, and the seller can provide Q that the buyer wants. And again, this Q, we are agnostic about what it really is. It can be interpreted as a good if it's households trading with each other or households trading with firms, but it can also be interpreted as an input in a production function, can be interpreted as an asset that is traded among these agents, can be interpreted as technology. So again, there have been many applications in the literature, and for our purposes, you can use any of them basically. Okay, so in the CM, centralized market, agents consume a good X and they supply labor H. A good X is produced by firms according to production function that depends on H, labor input, and K, capital input. We assume the CM is perfectly competitive, so the wage omega and the return on capital kappa are just given by the marginal products of labor and capital. And as in standard growth theory, X can be turned into capital 1-for-1, new capital is productive in the next period, and it depreciates at rate delta. Okay, so I already told you I have multiple assets, so and I introduced capital already, so let me introduce money and assets now. So M, money, is fiat money with supply growing at rate mu. And for the first part of the presentation, we assume that the mu is growing at a fixed rate, but then later I will also talk about interest rate pegs instead. Then A, the Lucas tree, is a fixed supply asset with dividend rho and typically interpreted as a fruit. And I already said K is reproducible capital, and it's used together with H to produce X. We denote the CM prices of these assets as phi M for the price of money in terms of real consumption goods, in terms of X, and phi A denotes the price of the Lucas tree, and phi K denotes the price of capital, but because it can be turned into the consumption good 1-for-1, the price is going to be always 1. And the portfolio is just zeta and contains M, A, and K, so the holdings of money, assets, and capital of an agent. Importantly, we assume that there's different acceptability and pledgeability of these assets. So alpha J is the probability of meeting a seller in the DM who accepts J, and J can be any of these 7 things in brackets. So meet a seller only accepts money, so that would be the alpha M gives that probability. You can meet a seller that only accepts assets. You can meet a seller that only accepts capital. You can meet a seller that accepts M and A, so accepts money and assets, or M and K, or A and K and E. Like typically, we will not have all of these 7 positive, but we have all of them in the model. But for example, in the quantitative exercise, we have only those positive that include money, like assuming that money is always accepted, but other assets might also be accepted. But in principle, you can also have these meetings where money is not accepted, but only another asset. And again, it depends on how you interpret the model. Sometimes if firms trade with each other, cash might not be the ideal payment instrument. Maybe they prefer using assets to pay each other. So these alphas capture liquidity on the extensive margin. We also include an intensive margin. This is denoted with chi. So chi J. Here, J can only be M, A, or K. This denotes how much. So given a seller accepts asset J, how much of it they accept. So they might only accept a fraction of that asset. This can be interpreted as a pledgeability constraint because actually in the model, it is equivalent where the trade is direct in the sense that agents give assets and directly receive consumption, or whether trade is basically collateralized credit. So especially when you use A or K, maybe collateralized credit is the more standard way of thinking about this. And the equations are exactly the same, so you can interpret it either way. Okay, I will skip most of the derivation of the equilibrium, but on this slide here, I want to tell you how we denote liquidity. So Z is going to be a measure of liquidity. Zm is liquidity entailed in money holdings. So Z is the real amount of money. So phi M, remember, is the price of money in terms of real goods. M is the money holdings of an agent. And then Chi-M is the pledgeability. So this is basically the pledgeable part of the money holdings of an agent in real terms. The same for A, for the asset. So for the asset, it's the price of the asset in the next CM plus the dividend earned on the asset times the asset holdings, and again multiplied by the pledgeability. Because if the asset is only partially pledgeable, then liquidity is not the full amount of the asset, but only the pledgeable part. And for capital, it's 1 plus the return on capital minus the depreciation rate, again multiplied with the pledgeability. And then the liquidity positions in the meetings where several assets are accepted are just the sums of these. So in a MA meeting, liquidity position is ZM plus ZA, and so on for everything. Oh, by the way, and we have an E meeting is a meeting where the seller accepts everything. So just to explain why we use E is a meeting where everything is accepted. Okay, we don't specify. We allow for several payment mechanisms, but I won't go into these details. For most of what we do, actually, we do take it or leave it offers, which is actually equivalent to valuation pricing. But for some applications, we use different pricing mechanisms, especially for when we do the welfare cost of inflation, we consider different mechanisms. Okay, here's the definition of equilibrium, but more importantly, here's the Euler equation for money. So, like liquidity value of money is given by discount factor beta over the inflation rate times the value of money tomorrow, and then the term in bracket basically captures liquidity. And liquidity is depends on all the meetings where money is accepted and the liquidity premium in these meetings. So if you're familiar with these Lagos-Wright models, this might look standard, otherwise maybe not. So unfortunately, I don't have time to go into details, but this is basically the value of money is augmented by liquidity, and the same is true for assets and capital. So for assets, it might be relatively standard. So if all liquidity premia are zero, like if there's no liquidity value to capital, either because capital is not liquid, all the alphas where A is included are zero, or because in all meetings where capital is accepted, liquidity is not scarce, and the asset is just going to be priced fundamentally. But if there's a liquidity premium, then the asset price might increase. And I mean, here we put these Euler equations in terms of the liquidity position, but you can also rewrite them in terms of the asset price, and then you really get the fundamental price, which is just a function of the fruit and the discount factor. But yeah, it might be then augmented by liquidity. And the same is true for capital down here. Right, okay, let me turn to steady state results. So here are the comparative statics. So we derive carefully all comparative statics in regards to iota, which is the opportunity cost of holding fiat money. Rho is the dividend earned on the Lucas tree, and epsilon is a productivity parameter of capital. And so one thing we can show is the direct effect, like higher iota means higher opportunity cost of holding money, so that reduces the holdings of money. Higher rho, higher dividend for the asset makes the asset more attractive, so this increases the asset holdings. Higher epsilon, higher marginal productivity of capital makes capital more attractive, increases holdings of capital. So these effects are unambiguous. The cross effects, there we have these numbers, and they say that like, we know it's positive under some conditions. I'll go into more details on that on the next slide. Basically, the direct effects are unambiguous. The cross effects, they depend on how these assets interact in other meetings. So here's an example. So here you see, so on the x-axis, we vary inflation, basically, so we make money less attractive. You see that ZM goes down, of course, agents want to hold less money. And instead, because in some meetings, instead of using money, agents can use assets or capital. So to make up for lower holdings of money, instead want to increase asset holdings and capital holdings. So this is more or less the standard result. And also all returns go down. But actually, we can have cases, because we have three assets, where this is not case where, so again, money goes down. And in this case now, asset holdings go up a lot. In fact, they go up so much that capital holdings go down. So the story here is the following. Inflation makes money less attractive. And if there are meetings where agents can use money and assets, as a reaction to that, they might want to hold more assets to make up for that. And if the increase in the asset holdings are so high, and if there are also meetings where agents can use assets and capital, then it turns out that maybe you can have a case where asset holdings go up so much that agents also want to reduce capital holdings instead. So this is the Mandel-Tobin effect, basically. So under some conditions, we have the classic Mandel-Tobin effect, where higher inflation gives you higher investment in capital. But if assets and capital interact with each other in the payment process, you can have cases where you have a reverse Mandel-Tobin effect, where higher inflation lowers capital holdings. The same can happen for assets, actually. And also, like here, assets are always increasing in money, but we can also find parameters where actually capital is increasing a lot and then assets are going down. And to find results like this, you really need all the three assets, because with two assets, you cannot find such results. Okay, yeah, we have more takeaways here, but in the interest of time, I'm gonna skip ahead, go to dynamics instead. First, one asset dynamics. So in general, a nice feature of the model is that depending on the alphas we choose, we can basically shut down interactions between certain assets. And in particular, if we set all the alphas to 0 where more than one asset is accepted, we end up with actually basically three separate models, or with still one model, but each asset is going to be priced independently, because these assets don't interact in the payment process. If they're never substitutes, then each asset price is completely independent of the other asset prices. So we can analyze them as if they were the only asset. So under these configurations, we can retain standard results. And for example, for money, we can show that there are two steady states, one where money has a positive value and one where money has a value of 0. There can be dynamic equilibria where the value of money goes to 0. There can be also cyclic, chaotic, and transport equilibrium. So these results are known in the literature. Same for assets. So assets have a single steady state because of the positive fruit. You always want to, like, there's no case where the asset value goes to 0 because the asset pays this fruit, this dividend. But still, you can have cycles and sunspots for assets. For capital, the way we model capital here, so importantly, should have mentioned that here we assume the production function is additively separable in labor and capital. So we also consider other cases, but sometimes we use this just to shut down effects going through the wage that would have general equilibrium effects that would complicate the analysis. And here we basically do it to actually make our life harder, in the sense that here capital cannot cycle, because the Euler equation for capital, the third one here, it's not a difference equation. So this is just an equation of set k t plus 1, but set t does not show up. So the decision for capital holdings are actually static under these configurations. So when capital is the only liquid asset, there are no dynamics possible. If we allow money and assets to interact, there can actually already be a lot of cyclical equilibria. So we can find 4 types of cyclical equilibria for the same parameters. So they all coexist, and a theory cannot predict which one is more likely to exist if parameters are such that they exist. And actually, because both money and assets can be be in a 2 cycle when they're the only asset. So basically, what we show here is that when they both interact, you can have like all 4 combinations that are possible. Like money can be in a steady state, whereas the asset is in a 2 cycle. The asset can be in a steady state, whereas money is in a 2 cycle, or both can be in a 2 cycle with either positive or negative correlation. So when one of these payment instruments cycles, the other one has to cycle a bit too. But in some equilibria, one is almost constant, whereas the other cycles a lot, and in some of these equilibria, both cycle a lot. So this means that between money and assets, like all kinds of correlations are actually possible in dynamic equilibrium. And we also show that when K interacts with either M or A, we can have cycles in K. So even though F is linear, we can find cycles in K once capital interacts with money. As long as it does not also interact with the asset A, correlation has to be negative. So only once we go to 3 assets, we can have even more patterns. And yeah, similar results when A and K interact. Okay, so with 3 asset dynamics, again, for one set of parameters, we can find numerous different cycles. So I can show them graphically on the next slide. So here, I think on the left-hand side, they coexist for the same parameters, whereas parameters are slightly different for the one on the right. But basically, you can get all kinds of correlations with 3 assets. In the left one, money and assets are positively correlated, whereas capital is negatively correlated with both of them. In the middle one, money and assets are negatively correlated, whereas assets are positively correlated with capital. And then the third one has capital and money positively correlated and negatively correlated with assets. And here is also this Lucas critique application that I mentioned. So in the left panel, going back, we have positive correlation between money and assets. But actually for the econometrician would now want to think about how to increase asset prices. He would say, okay, this graph tells us, this time series tells us we should lower IOTA, the opportunity cost of holding money. That will increase ZM. And in turn, because correlation is positive between ZM and ZA, this will also increase asset holdings and the asset price. But actually, for the parameters we use in this example, comparative statics are unambiguous. And actually, A is increasing in IOTA. So lowering IOTA will actually ZA instead of increasing as econometrician thought. This shows that the correlation observed over time does not imply policy effects go the same way. So this is a standard application of the Lucas critique. Okay, for the last bit of the presentation, I will talk about monetary policy. Very briefly about steady state. So in steady state, the inflation rate is equal to the growth rate of money. So pegging the growth rate of money is equivalent to pegging inflation or this nominal interest rate IOTA. The policymakers could also target one of the sets, like liquidity positions, or also one of the R's, like the return on capital or the return on assets, by letting mu be whatever it takes, basically looking at this graph we showed earlier. But of course, there are upper and lower bounds on the R's especially, but these bounds do not need to be 0. They can also be negative in some cases. Right, and also to hit a certain target for the return RJ, policymakers must be willing to bear the consequences. So, for example, in this figure 1, which is a numeric example, policymakers can lower the return on the asset from 5% to 2%, but this requires setting inflation up to 10%, which is typically bad for welfare. In dynamic equilibria, turns out that pegging the growth rate of money or this nominal interest rate is not equivalent. And when policy pegs the growth rate of mu, dynamic equilibria exist even if money is the only liquid asset. So the dynamic results I showed you before, they were for a constant money growth rate mu. If the policymakers instead peg IOTA, this rules out dynamic equilibria if money is the only liquid asset. But if money is not the only liquid asset, if money interacts with assets, for example, so if alpha M, alpha A, and alpha MA are all positive, then dynamic equilibria still exist even with fixed IOTA. And this generalizes to also having K liquid. So when K is also liquid, you can have dynamic equilibria even when policymakers fix IOTA, where all 3 payment instruments cycle. Okay, the very last bit about welfare. So we calibrate the model to match US money demand data from 1955 to 2008, and we can compare the welfare cost of inflation and also the welfare cost of eliminating currency across different setups. So we compare various bargaining mechanisms that give different pricing protocols in the DM, and some of them we calibrate to match markups. So these are our preferred calibrations. But maybe more importantly, we compare a model where we have these multiple liquid assets with a model where we have only money. So we set the probability of meeting someone equal in both models, but in one model we only set alpha m positive, and on the other model we set all alphas containing money positive, but also so that sometimes agents can also use assets and capital. So here is the,
you
yes.
should be wrapping up. You're already over time a couple of minutes.
Okay, yeah. Okay, let me go to the conclusion slide. So maybe just to take I can finish on this one. So yeah, the welfare cost of implication, it varies with specifications, but it's always substantial. Importantly, it's high with multiple assets. And welfare cost of 10% implication is 1.5% under CALI, 3.5% under Nash if we match markups. And the welfare cost of eliminating currency is substantial too. It varies from 6% to 20%. Okay, yeah, that's it. Thanks a lot for your attention. I guess I will stop sharing.
Thanks for a very interesting presentation. Well, now I'm going to share my screen. Okay, I'm gonna present this paper. We changed the name. It's Rational Sentiments and Financial Frictions now. Joint work with Peyman Khorrami, who's at Imperial College. I'm at the Central Bank of Chile, so usual disclaimer applies. These are just our views. Okay, at least for the last 10 years, there has been an explosion in this macro literature that tries to incorporate the financial sector into it. Here are a list of some examples. And despite all the success in understanding the role of financial frictions, there are still some challenges for this literature. Here I highlight a couple of them. First, the literature has a hard time reproducing the severity and suddenness of financial crisis. And the path that it has taken is to add systemic bank runs. And I myself have some work on it. And basically the idea there is that there's a failure of coordination, and everybody and the wealth of the financial sector is wiped out, and this has like very sudden and very severe effects on the economy. Another challenge is that for these models it's very hard to generate booms that are prone to bust. No, in the data you can see that actually financial crises are predicted by credit booms, for example, and you usually see that interest rates are the risk premium is very low before crisis. These kind of features are very hard to predict in these models, because in these models, usually after a sequence of good shocks and that generate a boom, a crisis is actually less likely. So what the literature has done, for example, is to add non-rational beliefs. No, these they add either extrapolative expectation, diagnostic expectation, some kind of error in what agents are expecting in order to reproduce these features. So in this paper, we're not going to take these routes. We're going to take a complementary approach. And what we're going to do broadly two things. So first, we're going to say, we're going to take a bare bone example of this class of models. And what we're going to show is that there's a set of unsteady equilibria that are going to be sunspot equilibria in this kind of model. So without adding anything, just to take a standard example of these models, we're going to show that, and we're going to illustrate how this mechanism works that creates this multiplicity. And then we're going to argue that actually this class of equilibria are interesting because they can potentially help you to alleviate concerns. And we're going to present how this kind of equilibria can alleviate concerns, challenges 1 and 2 that I listed here. Okay, so that's the paper. Let me jump directly into it. The model. Okay, so a very common macrofinance setting, all agents are going to have log utility over consumption. There are going to be these classic two groups, productive and unproductive. We're going to call productive experts and productive households. Both use capital with a linear technology in order to produce the final good. Capital, the only physical asset in this economy, is going to be traded at price Q, and it's going to evolve according to the equation that you can see there. G is just a constant, so the stress and drift, and this Brownian shock, this Z1, is gonna be our fundamental shock. So you can think of it as a, I don't know, TFP shock if you want. You know, this is classical in this kind of models. You have the shock to the capital quantity, which you can think of as capital quality. Okay, so if I were, so this is basically that's kind of the entire setting. If I were to solve this with complete markets, this would collapse to a standard growth, to a version of the standard growth model. The productive agent hold the entire capital in the economy. We share a risk through financial markets, and nothing really interesting is going on. Of course, we're not going to do that. We're going to impose a financial friction that's going to be that producers cannot issue equity. Okay, so it means that there's going to be, in some sense, the risk sharing through financial markets is limited. That's going to be key. They will be able, everyone is going to be able to borrow and lend at a risk-free rate. Just let me highlight that there are no credit constraints where the capital price is in it, and because that's a way of generating multiplicity, we're not going to go there. All resorts are going to generalize if we have some equity issuance. The important thing is that it's not complete market, so there's some degree of financial friction. And importantly, information structure, we're going to have, besides the fundamental shock, we're going to have this extrinsic uncertainty, which we call, which is going to be captured, it's going to be represented by the second Brownian motion, is DC2. Okay, so that by eccentric I mean that there's nothing. It doesn't affect preference. It doesn't affect production, technology, anything. It's just something that is moving out there, has no influence over any of the fundamentals in the model. Okay, so let me set a little bit of notation. Capital price, evolution of capital price is a conjecture of the solution, has some expected return and has some loading on the fundamental shock and some potential loading on the sunspot shock. For these objects are going to be endogenous. This loading on the fundamental shock is usually called amplification. Why? You can see it below. What you have below is the what we're gonna call the volatility of capital returns, this sigma r squared, and it has the fundamental component. Sorry, the fundamental component, which is associated to the shock itself, to the to capital, and the amplification term that's going to be associated with the capital price. Okay, so this is a little bit of notation. Just let me attempt something very heroic in this short presentation. I'm going to show you the entire equilibrium in one slide. I'm not going to go into detail. Let me mention these two key equations. So the first one is what we call the price output relationship, and it basically is goods, market clear for goods. On the left hand side you have aggregate consumption. There's no investment here, so it's, since everybody's log, it's just discount rate times just wealth. This is, everything is divided by the aggregate level of capital, so you have just the price of capital del. And the right hand side is output, is just output that's going to depend on this kappa, which is the share of capital that's managed by experts. Of course, more capital managed by the productive agent, more production there. The second equation is the risk balance condition. It just says that when both agents are holding capital, the difference in returns, which is the left hand side, has to be compensated by a difference in required returns, which is associated with the volatility of the asset and how much leverage do I have. This eta here that appears is the expert's wealth share, and kappa over eta, the amount of capital they have over their wealth share, is going to be a measure of leverage. Okay, so I'm not going to talk about the rest of the equations that are going to appear here. Let me just say that this is the entire thing that the equilibrium impose on our economy, meaning that when you do optimization market clear, this is what you're going to get. And the point, one point here is that the only state variable, you could construct an equilibrium in which the only state variable is the wealth share. So the model is designed to do that for simplicity, and that's the key state variable in the literature that I have referred to in the first slide. Okay, so an equilibrium is just going to be, given some initial wealth share, you have a process for prices, which are Q and R, allocation, which is this kappa, such that all the equations above hold, and that's the entire equilibrium. Okay, so now I'm gonna what do we usually do to solve this thing? So we usually take the path to the left here. So we say, okay, the only state variable that I need it's this well share. So I'm going to impose that this is Markov in eta. And then I'm not going to care about this extrinsic uncertainty, this weird thing that I said about the DZ2, the second Brownian motion. And so we said that there basically it's insensitive to the second Brownian motion. And that's what we're going to call fundamental equilibrium. So that's what we do usually. So the usual solution path, we impose this, and we get an extra set of conditions from this step, from the solution concept, that are, if you're familiar with the literature called Ito's lemma, that says basically the dynamics of Q, of the dynamics of early endogenous objects must be consistent with the dynamics of eta, or the dynamics of the state. Okay. Okay, but so even when we impose that this is Markov in eta, we could conjecture, we could try to find an equilibrium in which that DZ2, this second Brownian motion has some role. So it will be go here in this graph, you go to this, and this is what we call well-driven Bayesian-Sunspot equilibrium. But it turns out in our paper, we show that as long as you have some fundamental uncertainty, this is not going to work. So basically, this solution, this kind of equilibrium, this WBCE are going to be inconsistent with fundamental shocks. So basically, once you impose Markov, you either have the solution that we always talked about, or and you're not going to be able to give a meaningful role to this extrinsic uncertainty. So the conclusion is that once you impose this Markov in eta, you are not going to have interesting dynamics, interesting at least new dynamics to the literature. Okay, we have a minor result that you can actually control this well-driven BCE when sigma is 0, but that's kind of a naive edge case. So we're going to have to take a different route in order to generate interesting result and interesting dynamics, and that's what we're going to call going to the right to the sentiment-driven Bayesian-Sunspot equilibrium. Okay, but first let me remind you a little bit how these solutions look like in the literature. So what I have here is the capital price is the key endogenous object as a function of the well share. And what you have on the black line is this, what we always solve at the fundamental equilibrium. You have that when the well share is low, capital price is low, there's going to be fire sales every time the well share moves around, that's going to move the capital price violently. And you're going to generate some endogenous amplification there. On the other hand, when well share is high, kappa equal 1, meaning the expert managed the entire capital in the economy, and price is not very sensitive to movements in eta. Okay, so that's what we usually have. Now, what we're going to show is that we can go beyond wealth as a state and have what we are going to call sentiment-driven Bayesian-Sunspot equilibrium. And this is the main theorem of the paper. Basically, we show that under Meyer parameter restrictions, we can have an equilibrium that lives in this triangle. So these two lines, or this black line is the one that I was describing before, this fundamental equilibrium. And this triangle is basically all, so instead of having now a function from well share to capital price, I have a star correspondence. I have a range of capital price that can be consistent with this well share. And this is going to allow for way more possibilities for a given well share. You can have different capital prices, you're going to have different volatilities. So there's going to be much more flexibility for the model or for the equilibrium solution to generate interesting dynamics. So what you have here and the upper bound is the capital price associated with efficient allocation, basically all capital managed by the expert. And what you have below is when experts hold capital proportional to their wealth, meaning that they are not using any leverage. Okay, and what you're going to have the color in this picture is the volatility of capital returns. You have and as you can see here, is actually truncated because volatility is unbounded near the lower bound. So basically, the only way to convince these guys to not take leverage despite their productivity advantage is if volatility is very high. Just for a comparison, the fundamental equilibrium, the maximum volatility that you could have there is around 0.2, and you can see that it's that there is a relatively low volatility in terms of what you can get in this kind of equilibrium construction, in this sentiment-driven by BSC. Okay, so let me give you in this short presentation a little the intuition on how can I where this multiplicity or this multiplicity is coming from. So remember the price output relationship, you can think of it as a supply. Basically, it says that the higher the capital controlled by the productive agent, the higher is going to be its price. That's a blue line there. And the resource balance condition is like a capital demand or relative capital demand. So it's basically, if you want the expert to hold a larger share of the capital, they have to face a lower price. So their excess return is, so their difference in return is greater. Now here, if you see these two equations holding constant the distribution of the distribution of wealth, holding constant this eta, you still have 1 degree of freedom, which is this volatility of capital returns. So, and this is what it's going to be key here. So you can have an equilibrium if the volatility of capital returns is some value, or you can have an equilibrium if the volatility, for example, here is greater. So a greater volatility of capital return is going to be consistent with a lower capital price and a lower efficiency in the allocation of capital. So meaning that you can have these movements in sentiment, these movements in fear, and still be consistent with equilibrium. Okay, so this is kind of a static view of where the multiplicity is coming from. It's also important to check that this static multiplicity has a dynamic stability, meaning that it's not going to lead to a path that violates equilibrium conditions at some point. Okay, and the way so the form that statement is equivalent to say that basically you have to check that the dynamics do not leave the triangle that I draw in the previous slide. And that's going to be relatively easy in this kind of model. Why? Because the set of equilibrium conditions is only going to discipline the risk premium, but not the expected return on capital from and the risk-free interest rate separately. So you have 1 degree of freedom when you construct this equilibrium that you can use to provide this dynamic stability. So you can think of this, choosing this mu q in a straightforward way, where you just put mu q very high when capital price is low, or this mu q very negative when capital price rises. Now, importantly, in continuous time, this is going to be tractable because this kind of stability requirements are going to translate just to boundary conditions. Basically, I'm going to have some boundary conditions on the triangle that I showed. Yeah, so what I was saying is that when capital price is going up, you just set mu q negative, so it goes down. When it's going down, you just set mu q positive, so that it comes up again. So that's gonna discipline just the boundaries of this, and this is gonna, and the fact that it just discipline these boundaries is gonna provide some indeterminacy within this class of models that are gonna deliver some interesting results. So let me just mention quickly. So you have this decoupling result basically says that in the entire triangle I showed you, the volatility of capital returns is pinned down, but the decomposition of this volatility of capital returns between the fundamentals, the one associated with the fundamental shock and the one associated with the extrinsic shock, so basically with the two Brownian motions, is not pinned down. So you can basically construct an equilibrium in which you can assign a target share for each one. And the other one, it's the in terms of the drift. What I was saying, you just need this mu q to follow some restriction in order to get stability, but those restrictions only applies near the boundaries of our construction. So within the interior of this set, you basically can have any kind of dynamics for Q, or at least for the drift of Q, let's say. Okay, so that's our big construction. And now let me just check. Okay, let me just try to do this in 5 minutes. So what I'm gonna do is I'm gonna now do some constructions, some specific construction in order to address some of the puzzles. So let me just now, I'm gonna put this S is gonna be, it's gonna be completely extrinsic to the model, just gonna load on this shock that we had before. And this is gonna be our idea of our sentiment, okay? And then we're gonna construct a Markov equilibrium. There's gonna be Markov in eta and S. We add an auxiliary, a third state variable that's gonna just apply for the drift, just to get some of the dynamics afterwards, but that's not important. We're going to allow for this S to have an endogenous dynamics, and I could make a case that this is sensible because when you forecast your condition on price, and price is going to depend on wealth, so your beliefs are going to depend on wealth. And this allows us for a very nice construction in which you just can conjecture the Q function as a function of eta and S, and then just back out the volatility of the beliefs that justifies this. So here is our construction. You have the capital price. You have basically on one side of S, you have wealth share, and this S, this sans possessive, the rational sentiment in the other axis. So to one side you have the fundamental equilibrium, and to the other you have this terrible equilibrium. And basically what we do is use S to just make an average between them. Then you can so basically the larger S, the worse is the equilibrium. So it's a measure of some pessimism, if you want. So larger S, you have larger return, and here and to the right hand side you just have the sunspot volatility that justifies the equilibrium construction. Now let me just show you some of the dynamics that this can generate. Here I graph the fundamental or the balance sheet bust, which means that what happens for the dynamics with low eta versus the dynamics of a non-fundamental bust, which is the dynamics of a large S, right? So, and these graphs are constructed such that the initial drop in capital price is roughly the same. What you can see here is that this kind of the two kind of recessions look very differently. And we did not this non-fundamental recession look a little bit closer to the date in the sense that they generate larger volatility spikes, and they kind of have not so protracted recessions. They come back more aligned with the data. Okay. So we do have some propositions within this our construction. We can, if you give me a target volatility for the capital returns, I can generate an equilibrium that actually matches that. If you give me another interesting thing here is that even though I can increase the volatility of capital returns as much as I want with my construction, actually when I do this, the share, the larger the volatility of capital returns, the larger is going to be the share associated with the non-fundamental shock. So in this construction with S, and so you have the decoupling. Actually, the more you're going to have you can have a lot of volatility of capital returns, but actually the volatility associated with fundamentals going to be going down. Okay. Now for the boom predicting crisis is just. This is where we use our second state variable and these following models with extrapolative belief. We just define if this X that is a cumulative of the extrinsic shocks. Basically, if you have a series of good shocks, then this X is going to accumulate these shocks and see where the sentiment kind of is, right? And so with that construction and a negative dependence of the drift of S on this X, what's going to happen is that after a series of good sentiment shocks, which is this negative, X and the sentiment is going to be low. You're going to have meaning that pessimism is going to be low. You're in booming times, but this is going to shift the conditional distribution of the future because this is going to basically push the drift of S. So basically what it's saying is that in the future, I'm going to have more pessimism. It's the same idea that this behavioral extrapolative expectation model have, but everything here is rational. Okay. And what you have, so here I'm going to make the argument that these graphs kind of tells you that in our model, booms can potentially predict crisis. So what you have is the input responses on the capital price, the volatility, and the probability that the volatility is super high. And we construct two different booms, one with eta high, so very well capitalized, so this strong balance sheets, and the other one which a very good sentiment, which is lowest. So the one with a very good sentiment, you can see that after this boom, you get, and we are graphing the difference with, so we start, so we graph the difference with respect to the path on the started at the same point. So what you have here is that after a boom, you can see that what happens on average. So this is after like we ran like 10,000 years of simulation. You have the capital price after a boom. The capital price in a couple of years probably is going to be below the unconditional mean, and the volatility in the boom is low, but you see that it's going to go up and be above the unconditional mean. And more importantly, more clearly than the volatility, you can see that the probability of the volatility is really high. So this volatility of crisis is actually in a couple of years out of this is going to be very high. It's going to be sort of above the mean. Okay. We also have some. We also do here some more standard graph, which is the behavior of financial crisis. We just identify financial crisis as the bottom 3% of the bottom 3% of the change in output here. So these very bad situations, how do they look like? Well, they look like they're preceded by high capital prices, by low volatility, and by low risk premium. Most what we see in the data, we have a sharp drop in capital price once the crisis arrive, and then you recover, and a sharp spike in volatility of capital returns and risk premium. So this is more aligned with the data. Okay, so I'm not going to talk about this. I did everything with Brownian motions on the paper. We have a section in the paper where is sentiment-based jumps. So basically, instead of having extrinsic uncertainty in form of a Brownian motion, we have extrinsic uncertainty in the form of a jump, and also generates can capture the dynamics around financial crisis very well. So let me just conclude. We have shown that macroeconomic models with enough friction inherently permit this sunspot volatility. This kind of model has extremely common, so we shouldn't be ignoring this phenomenon. Now, we provide a fully rational notion of sentiments and show that it's powerful in the sense that we can basically take these models as they are, just with a different solution concept, much closer to the data in terms of we generate unbounded amplification, sharp volatility spikes, and during boom and bust cycles. Now, our results calls for cautions in terms of the profession usually takes these models, numerical simulation of these models, and try to do policy exercises. What we're saying is that if we are right, the numerical procedure is implicitly selecting one of these equilibrium, and without any justification. So this might not be ideal, especially for policy exercises. So I mean, of course, one path here, and what we do not provide in this paper is a theory in which you say in which you provide some sort of selection mechanism for this equilibrium. We do not have that. That here it would be I think would be the right step forward, but it's also very challenging, this kind of model, to generate some sort of selection mechanism aligned with the frontier. Now, one thing that is important is that the policy consequences in this equilibrium can be very different from the policy consequences in other models. For example, if this is all, if this bust happen because of the sentiment that we can construct, then it's not really that, and it's an asset side phenomenon. Deposit insurance is not going to be really effective. It's not that I take out my money because I think that it's not going to be, they're not going to pay me. It's just that we all think that things are going to go bad, and things go bad at the end of the day. Also, if we decouple this from this well share, so it's not that things are going to go bad with when these guys are not very well capitalized, then capital requirements, bailouts, all these things are not going to have the same consequences. Okay, so with that, I close my presentation. Thanks everyone for listening. I think that we are gonna that the room is gonna be open for another 7 minutes in case there is questions about any of the presentations. We can talk for another 7 minutes, I think.
Thanks. Nice presentation. It was interesting.
Oh, thanks. So if if there are no questions, I do have some questions, Lucas, about
Sure, yeah.
the presentation. So I'm not I do know this the kind of models, this Lagos Wright literature, and so what but I was a little bit lost in your exercise in the sense that okay, you give the option. So first, just to be sure, so you have some meetings in which you can accept one or the other. So that's going to be endogenous, or you kind of have like some share of meetings that's going to accept one asset or the other.
No, yeah, sorry. These are exogenous in our model. There are other papers that endogenize these, so this can be done, but we just take them exogenous, exactly.
Okay, so there's a share in which you have like 7 combinations. It's going to be a share associated with each.
Right.
No, that's fine. I just wanted to understand.
Sure.
And then, so you said like you have generate cycles. There's no aggregate uncertainty, right? As in the original paper.
No, exactly. It's all deterministic. So yeah, that's something we thought about actually. Also adding aggregate uncertainty on top of that, which I mean we expect that then you could, I mean of course then you could have fundamental dynamics, but then on top of that also like these belief-driven dynamics basically, which is I guess related to what you were.
Yeah, and it's a little bit it's usually a little bit, and the next question is related to what I've been thinking with this paper is that okay, we do not have a selection mechanism either, and what we do is we try to illustrate. Look, we have a bunch of equilibriums that look like the data, so that's why we are trying that, and that's kind of the approach we're taking. So are you taking any like approach in terms of which equilibrium looks similar to data or which equilibrium can be selected by any mechanism?
No, so for the dynamic part, we don't really look at the data. So the stuff where we do numerical exercises and the small calibration is about steady states. For the dynamics, we also don't select equilibria. We just say basically many equilibria are possible. To match the data with the dynamic part of the paper, we would still want more features to be closer to the data, especially like fundamental shocks, which we don't have. That's why we don't take that to the data. Our point is just that like our models are still relatively simple because once you start adding fundamental shocks and things like that, things get even more complicated. Our point is a bit like, even in these somewhat simple models, we find lots of dynamic equilibria, and our guess or our conjecture is that once you add shocks and bring these models closer to reality, we'll even see more dynamics. So our point is also similar to yours, a point of caution that we shouldn't just think we can select a steady state equilibrium or a specific dynamic equilibrium, because many various equilibria exist.
Yeah, I mean, I do get the point, but I wasn't trying to push you to incorporate like real features into the model. I was trying to push you like you have like this bunch of dynamics. Like, of course, these models, nor your or my model, is built to do quantitative exercises seriously, but qualitative features of the data that can be captured by this type of equilibrium. I think that would help to connect.
Yeah, sure. Yeah, so I mean, what I showed was mostly these two-cycle equilibria, but it's easy to extend that to sunspot equilibria. So everything we do in 2 cycles can be sunspots, and I guess sunspots are definitely closer to the data than like 2 cycles. They are just too deterministic. Things cycle very deterministically. But once you go to sunspots, you can have more random cycles or more random dynamics. And I think there, I mean, the graphs I showed where like assets correlate in various ways. I think certainly one of them will be close to the data. I'm not sure about how the data looks like, but I guess since we can have all combinations, certainly one will be able to match the data.
Yeah, that's true. Perhaps you can zoom in some phenomena that it's not previously described by theory, and then just make. I'm just thinking about like how
these are good suggestions.
The paper, for example, like correlations. I mean, we do know that every kind of all assets like prices go down during downturns. You have this positive correlation in a sense. Yeah, it could be very interesting. Yeah, I mean, I don't know how to add like aggregate uncertainty on top of this, but then you can see like how do they behave you know, when things are going down, maybe one asset's going up, and then you can think of that as like sort of like it's gonna have like some sort of safety premium or something like that.
Right. Yeah.
But yeah, no, it was interesting presentation.
Thanks a lot.
Thank you. Okay, I think that if there are no more questions, we can close our meeting here. Okay, thanks,
Yeah.
Lucas. Thanks, Philip.
Thank you. Interesting talks.
Thank you.
Thank you. Bye-bye.
Bye.